So welcome on this this early hour at JFOL to my session, getting into the flow, building applications with Reactive Streams. Now my bet is that during this session there will be several people walking in because of the early hour. So do not let them disturb you. What I will try to do for you today is to introduce you into the world of Reactive Streams, to tell you what it's about, to explain some of the concepts that are behind it, some of the implementations of Reactive Streams and how you can use them, and show you code in order to get you started. So who am I? My name is Tim van Eijndhoven. I work at JPoint, a small consulting company, and I'm currently hired by the Dutch National Police. And during my assignments over the years, I have been working with Reactive Streams technologies for the past three to 4 years. So all the technologies that I will show you today I've worked with. Some I've worked more with than others, so I can tell you more about them than others. But if you are enthusiastic after this session and want to know more, maybe a bit more in depth or something, just come and find me and I'll be happy to chat with you. So Reactive Streams, first starting with the Reactive Streams initiative, which is an initiative that was started by several companies a couple of years ago who built technologies or frameworks to solve this problem, and they saw the need that it would probably be a good idea to have some interoperability between them, right? To not build their own standards, but try and find a set of interfaces that work, that can work together. So Reactive Streams is this initiative, and basically it provides a standard for asynchronous stream processing with non-blocking back pressure. And especially this asynchronous nature is important, and the non-blocking back pressure is important as well. But those are the key components that discern this technology from, for example, the streams in Java 8. And the other thing is that the initiative was aimed at finding a minimal set of interfaces. So instead of trying to build this whole explicit standard, they decided on what is the minimal set of interfaces that we have to define in order to ensure that technology A can work with technology B in this both asynchronous and non-blocking back pressure supporting way. So what it has become is basically, on one hand, is a Java API. So they defined a set of Java interfaces. And next to that, there's a specification. So in the interface itself, it's not you cannot grasp all the functional requirements that have to be ensured in this standard. So you cannot say you need this method, but you also have to say what the behavior of this method is in order to make these technologies work together. So there's a specification that goes along with it as well. They provide a technology compatibility kit, so basically a test suite which you can run on your own implementations, and that will test all these parts of the specification in order to ensure that your technology adheres to the contract that is being imposed. And it also offers you example implementation, so some basic implementations of the various components. And that's really interesting. If you would want to implement your own implementation of this, then I would suggest looking at the examples, because they're very well documented in code with why they're doing stuff in order to adhere to the specification. So Reactive Streams in its nature is basically about having a publisher, something that produces data or events, and a subscriber, something that is interested in these events and wants to do something with it. So basically there's a data flow between them, right? So data flows from the publisher to the subscriber, and data flows in a push way, right? So the publisher pushes the data to the subscriber. Now in between you can have processing steps, right? So maybe my publisher produces strings, and maybe I want to process them into some other object type, or maybe I want to parse them or whatever, and then provide my more domain-specific objects to my subscriber. That's all possible. So there can be one or many processors in between. And there has to be a control mechanism for the subscriber. So there's a push from publisher to subscriber, but the subscriber has to be able to have some form of control over publishing these events in order to tell the publisher what it can handle. So basically it gets a control which is called a subscription. So these are the 4 interfaces that are defined by the Reactive Streams specification. If we go more in depth into what these interfaces are, we have the publisher interface, which is, well, really small, right? It only has a subscribe method. And it takes a subscriber. So this is a, well, really easy interface to implement, right? This can't be difficult. Now, when you look at the implementations, which I will come to later, you will see that the implementation-specific publishers often have many more subscription methods. For example, taking lambdas as arguments to well, save you from having to build your own subscriber and call this method, just more for convenience. But this is the basic API. Then you have the subscriber, which has a number of methods, and these are basically methods to signal, to send signals to the subscriber. So you have the onComplete signal, which is raised by the publisher whenever the stream is completed, right? To signal, well, there's no more data coming. Then you have the onError and onNext signals, which basically signal there's an error or here's the next item, and the onSubscribe. And this is the first method that is called. So basically what happens is you will subscribe the subscriber to the publisher, and the publisher will then call the onSubscribe method, providing the subscription to the subscriber, right? So that gives the subscriber control. Then you have the processor, and basically this is an implementation of both the publisher and the subscriber, right? So it subscribes to the publisher on the one hand, and it is the publisher for the subscriber on the other hand. So it implements the same set of methods. And then you have the subscription. And this is also an interface that looks deceptively easy, but this is a really important one. So the subscriber has the ability to both cancel the publisher, to tell them, well, I'm no longer interested in your events, so you can stop providing them. And the other one is to signal the publisher that the subscriber is actually ready to receive a certain amount of events. So those are really easy interfaces, right? Should be easy to implement. Well, let's take a look. This is the GitHub page of the Reactive Streams, and what you see is, well, here's a specification for the publisher, and you see that, well, there's only one method, but there's a set of 11 constraints to the implementation of that method. And they all have to do with stuff like the asynchronicity, the fact that it has to listen to the request for demand, all sorts of implementations which are absolutely necessary to ensure that whenever these technologies work in conjunction with each other, that they can they have the same, or the Reactive Streams characteristic of asynchronicity and back pressure. The subscriber as well. So there are many constraints that you have to adhere to in order to implement such a Reactive Streams implementation. So it's deceptively easy. Now, a general sequence in Reactive Streams is as follows. So first you have the event that something is subscribed to the publisher. The next thing that happens is that the publisher will create a subscription, right? It will create the control in order to receive the signals from the subscriber that it can do something. then it will call the unsubscribe method on the subscriber, providing it with the subscription. So now the subscriber has a subscription, has the option to send a signal to the publisher that it's ready to receive a certain number of items. So it will request a certain amount. The publisher then will signal the amount of events that it has data, right? So each data element is sent in a new on-next event. And whenever an error occurs, it will send you an on-error event. And it will do so for the amount requested, if it has that amount of events in to generate or already generated in a buffer or whatever. But it will send not more data than is requested. So you get a loop, right? So I will ask for a certain amount of items, and I will receive a certain amount of items, and then again I will request the next batch of items when I'm ready. So there's a loop. And it's another thing that the subscriber can do. It can also tell, well, okay, I'm done with it. Cancel the whole publisher. I'm no longer interested in your events. Now, whenever the publisher is done, so all events are sent, there are no more events to be generated or in a buffer, it will send an incomplete event to the subscriber. So it knows, well, we're done here. It's okay to go on. So there are 3 implementations of Reactive Streams that I want to address today. The first one is RxJava. Then I will tell you a bit about Project Reactor and about Akka Streams. So RxJava is probably the most well-known implementation when it comes to Java development, because it was around about the earliest technology to do this. Akka Streams is more well-known when you're programming Scala, and Project Reactor is basically the new kid on the block, pushed and promoted by Spring and Pivotal, but it's been around for quite a few years already. So, by a show of hands, who has worked with RxJava before? Okay, some hands. Anyone work with Akka Streams? Okay. And Project Reactor? Okay, cool. So let me start with RxJava. So basically, RxJava is the Java implementation of reactive extensions. And reactive extensions is a technology that was invented at Microsoft or thereabouts. It's basically coming from the .NET ecosystem. And it has been adopted by several other languages. So there's a Java implementation, but there's also a JavaScript implementation and in other languages as well. So the RxJava, the Java version of the reactive extensions, is aimed mostly at Java 6. It's bound to do so for the coming time because it's been used on Android, and as far as I know, you're still bound to Java 6 type support for Android development. So it is quite mature, but it's also perhaps not the most modern implementation of Reactive Streams. It's currently on version 2, and this is an important thing to note because RxJava 1 has been around for quite a few years, and RxJava 2 is now, I think, about 2 or 3 years old. And RxJava 2 was the first implementation to fully adhere to the Reactive Streams specification. So in RxJava 1, there was already back pressure support for some producers, but not for all, resulting in all sorts of errors when back pressure was applied. And now with RxJava 2, they're really fully supporting Reactive Streams. And one of the web frameworks that uses RxJava is the Vertex framework. Anybody worked with Vertex before? Okay, well, there are really cool talks online to find out more about Vertex. It's a really neat framework. So RxJava, when it comes to implementing these Reactive Streams interfaces, it's basically about the flowable, which is the producer side or the publisher side, and the flowable processor and the flowable subscriber. And there are many implementations of subscription, because that's the subscription is mostly what defines the behavior of the type of how you want to receive the data. So there are other, well, publisher or publisher-like classes provided by RxJava, which are, for example, single and maybe or completable, and those are basically meant for, well, you want to use our stream operators, but you're not really processing a stream, but you're basically sending like a simple asynchronous signal. Then you can use those classes as well, but they are not implementations of Reactive Streams, so they do not support the mostly the back pressure part. So let's see how this looks like in code. So here I have a method. It's called RxDemo. Basically, we start with a flowable, which generates a set of integers. Right. So we use the range method to create a flowable that generates an integer from 0 to 99 in this case. And then you have, this creates the reactive stream in itself. And then you can operate on it. And those operators that are offered by the implementations of both RxJava and Project Reactor are really similar to the ones you know from Java 8 Streams. Anybody who has not worked with Java 8 Streams yet? Okay, so well, most of these operators at least look familiar to you. So we have a filter operator, for example. So this way I will filter out the odd numbers and only keep the even numbers. And then I will provide a grouping to group them in their with their groups of 10. I will flat map, which is also an operation that should be familiar. I flat map them into so that I will get a stream of these lists of these items. So when I start the flowable here, I have all these numbers as separate events, right? So each number is sent as a separate on next event. And from this point on, from this flat map on, I will have every list of 10 items as a separate event being sent to my subscriber. On every item that triggers an on next, I will print out to the console. And well, let me leave this out for now. So when I run this, oh, that's the wrong combination, this one. Okay, so this is a syntax error, of course, which you have all spotted. So this is nothing, exactly nothing, right? We do not see any output, there's nothing happening here. And one of the things that's causing this is because I did not subscribe. So the publisher will only send events whenever a subscription has been made. So I will subscribe to the publisher here. Let me run it again. And then we have all these groups of numbers. And one of the things to note here is that I printed the thread name as the first item on the system out, and the thread is main. And this means that this code currently is being run on the main thread, right? On the one thread that is started when the application started. So this means that it's not asynchronous by default, right? This is just a synchronous and blocking way to execute this stream. So one of the things that it's partly due to the way I create the flowable, because it's more optimal to run this on the one thread. You have, when you create flowables, for example, which you generate with the use of a timer, so you say send an event every X seconds or whatever, then it will actually execute on a different thread, because that wouldn't make sense to block the main thread with it. But in this case, it will basically just follow the synchronous and blocking wave execution. But I can tell it to execute on a different thread. So basically what I can tell is say, well, subscribe on a certain thread. I will come to that a bit later in the presentation. But this way it will become asynchronous. So now when I run this example, you will see no output. And that's not because the flowable or the reactive stream has not run. No, it's because the main thread exits actually before the asynchronous processing of the stream has culminated into giving us output. So when I sleep the thread, you will see that the output is there. So this is the asynchronicity, right? So this way you can create these streams and they will execute in an asynchronous fashion. Okay. So now we get to Project Reactor, which is a project from Pivotal. I'm not sure if it actually was started by Pivotal as well, but currently it's in the Pivotal under Pivotal control, and it's used by Spring 5. So anybody been using Spring 5 or Spring Boot 2 with Webflux? Okay, right. So Project Reactor actually powers the whole Webflux stuff that they do. It's currently on version 3. So as I said, most of us have only heard of it in the last year. But it's been around for quite a few years more. And there's a really cool feature in Project Reactor, which is it allows you to pass a context. So one of the things that, well, it's especially convenient when you're using the whole Webflux stack, because previously what we did in Spring, or what was often done in Spring, was actually use, for example, thread local to store certain values that were used across the calls. But that's no longer possible when you're using Reactive Streams, because in Reactive Streams, you're not, well, you can be in control on what thread it executes, but most of the time we're not. So it will hop from thread to thread, eliminating the use of thread local. And this feature to pass context actually allows you to, in the Reactive Stream lifecycle, to pass this context object along in order to provide some of that same functionality. So that's a really neat feature. The types that we're talking about in Project Reactor are basically the flux for a stream of many items, or mono for a stream of one. It has a flux processor, and then there's a core subscriber, and there are different types of subscribers under it. But those are the basic classes. Now, when we go to the code with Reactor, what we will see is that basically it looks really similar to RxJava. I mean, there's almost no difference at all. And this is no coincidence. I mean, the RxJava 2 and Reactor, they've been speaking a lot on their latest implementations and trying to make it as easy as possible. And it's also no coincidence that this is very similar to Java 8 streams, right? So it's all familiar to you. Now let's execute the Reactor stuff, and what you will see is that basically it does the same. It has a different name for the thread, but that's it. So those are two technologies which are basically really interchangeable, so to say. And when it comes to Akka Streams, this one is the, well, in my list of three, this one is the odd one out, because Akka Streams has a different philosophy on, underlying the implementation. Akka Streams is a project from Lightband. and it's part of the whole Akka ecosystem. So it's basically a Streams implementation built on the Akka actor system. It's built in Scala, but it offers a Java DSL. So it's also very easy to work with from Java code. And one of the, in my opinion, killer features about Akka Streams is that it has the Alpaca library. And the Alpaca library is a library that consists of all different types of connectors to other systems, right? So we have connectors to certain certain types of databases, or to Amazon services, or what have you, Elasticsearch, Kafka, all types of external systems. So you can these are provided out of the box. These provide both publishers and subscribers, so you can easily tie them into your stream processing to send data into a database or read data from a database with the whole Reactive Stream support with it. And in Akka Streams, I was telling you about, well, it offers the publishers and the subscribers, but in the whole Akka Streams language, it's all about sources and sinks. So sources generate the events, and sinks actually process the events or receive the events. And you can convert these sources and sinks into the Reactive Streams types. So what does Akka Streams look like? Well, basically it starts with a source, right, which also has this range operator. Now, on the contrary to in both Rx and Reactor, the second argument to the range operator is the amount of items you want to generate. In this case, it's the last item you want to generate, so it generates all in between. We also have this filter operation and this group by operation. And this group by operation is already perhaps a bit different, because you have to tell what the maximum amount of groups is that it can use to collect the values. And now, in order to create the list of items that I want to have, I will have to, in this what's called a substream, I will have to actually wait for a certain amount of items to come along and then build this list. And I'm telling this to either wait for 100 items to create my collection, or whenever the substream is completed, it will also create a collection. So I have to do a bit more work in order to get to the stream of lists that I want to have. And then I have to merge the substreams back into the main stream. So basically what happens is it fans out, right? So you have one stream to start with, and then whenever you do the grouping, it will fan out into 10 substreams, or at most 10 substreams, and then it will have to come together again to the mainstream with merged substreams. And then I have to print it out. And well, I'm not the expert on Akka Streams in our team. Well, he's not here. It's too early, I think. But if you want to know more about Akka Streams, I can refer you to my colleague Laszlo. He's probably the expert on this stuff. So I do not know of a do on next function for Akka Streams. So I abuse the map function here in order to print out the item. And then in the end, I run it with to a sink, which does nothing, right? Similar to the empty subscribe that I called on Rx and Reactor. And I provide it with the actor system to execute on. Basically, it runs on actors and provides my list. Now there's you have the Reactive Streams specification, which provides a Java API. So there's a library with those interfaces. But since Java 9, Java actually has these interfaces as well. So the interface specification, which was provided by Reactive Streams, is adopted in Java 9. So from the standard Java library, these interfaces are provided. They're called the flow publisher, flow subscriber, flow subscription, and flow processor. It has exactly the same API, so basically you can interchange one for the other. And the implementations, the various implementations offer adapters to and from these types. And this is what actually allows the whole interoperability between these streams, right? So if we look at the combined usage, so the whole Reactive Streams initiative was there to ensure interoperability between these technologies that I just showed you separate, but we can combine them as well. So what we'll do here is we will start with Akka Streams. So we will create this range, and we will print the thread to show you that these steps are run on the whole Akka Streams stuff. And then we tell it to run into a sink, which can give us the publisher. So basically, this allows us to have this Akka Streams publisher here. Then we go to RxJava, and basically we take this publisher, right? We create a flowable from a publisher, and we will observe it on an Rx thread, because otherwise this will run on the Akka Streams thread. Right, so basically this code will run on the thread that is being used by the original publisher. Now when we say observe on, it will actually switch to the scheduler or a thread from the scheduler that we provided here. I will print out that it runs on an Rx thread in this case, or that we are in the Rx step. And here we're doing the filtering and the grouping and then the flat map into the list. Well, this provides me with a flowable, and flowable is an implementation of publisher. So then I will go to Reactor. I will create the flux from another publisher. I will again switch the thread to a Reactor thread, and then I will print out that I'm doing the Reactor stuff, and I will actually print out the list to the system out. And then in the end, I subscribe to the publisher, which is this Reactor publisher, and that in turn will actually subscribe to the Rx flowable, to the Akka Streams source. So now what you will see is that, well, basically we have the Akka thread. So every item that's emitted from the range triggers a printout on the Akka thread. Then we have Rx, which takes these emitted items and does stuff. So here you see that the Rx is already starting to run before Akka Streams is finished, right? So it's this whole chain is running in an asynchronous way. Then you have the Rx steps, and then in the end you have Reactor, which takes these items and prints them out to the app. So this way we can take stuff from one implementation and tie them into the stuff from the other implementation. Now there are drawbacks, of course, because for one we switch between these technologies. So within these implementations there are all sorts of optimizations which work whenever you use all the stuff from this implementation, but when you cross this boundary, these optimizations cannot be applied to that part of the stream. So you have a penalty. But well, it's a small price to pay. And this also allows you, for example, that Mongo, with its Mongo, the database with its reactive driver, also offers a Reactive Streams implementation. So you can actually write and read to and from the database directly with Reactive Streams provided types. So this is the Reactive Streams integration, and we have them with Java 9 Flow as well, which is a bit more verbose because both RxJava and Reactor implement the types from the Reactive Streams specification, but they do not implement the Java types. And basically they can't, because they both have to support Java, or Rx has to support Java 6, and Reactor has to support Java 8, in which these interfaces are not provided. So they have adapters. In Akka Streams, you have Java Flow support. In Rx, you have Flow Interop, which is a separate library that you have to use. And then Reactor offers the JDK Flow adapter. So this basically gives us the Java flow types, the flow publishers here and here, to provide the interoperability. And this does basically exactly the same. So currently, using the Reactive Streams API is probably the easiest, but whenever we all migrate to the newer Java versions, it will probably become the whole Java 9 flow stuff. So now I have some more advanced concepts underlying these technologies. So for one, back pressure. I've been talking about it, but what is back pressure and why is it needed? Well, suppose you start with a publisher which can provide you many items at a fast pace, right? It has a high capacity, and you have a subscriber which can only, well, process so much. So it has less capacity than the publisher can provide. It will send this large amount of data, right? Infinite amount of data to the subscriber. Anybody knows what happens to the subscriber in this case? It will die. And that makes me very sad. Okay, so let's try this again. So the people defining the whole Reactive Streams or building these systems, they notice that this has to be addressed, because this is a real concern. You have no control over many of the publishers that you tie into. So actually what happens is this whole control mechanism, right? So the subscriber tells the publisher, give me n items. I am ready to receive a certain amount of items from you. I have the capacity to process this amount of items now, currently. And then the publisher will send this amount of items to the subscriber. So this allows, well, sort of a negotiation between the subscriber and the publisher in how much data can flow from one to the other. And this is really cool, because this way you can actually, for example, when you take data from one source and put it into another source, you can have the whole, how many items can I actually have to read and have to send, and you can all leave that to the Reactive Streams. You do not have to really concern yourself with it, and this is really cool. Back pressure in real life. This is one of the things I like to think about when we're talking about back pressure. So it's not so much of actually pushing back, right? It's not so much that the subscriber pushes back to the publisher, but it's more of like a gateway. I'm ready for one car now to join the traffic jam. So this is basically what you can think about. Another underlying concern is scheduling. So I've shown you that it's not asynchronous by, or not all the implementations and every flowable that you create is asynchronous by default. Subscription by default happens on the calling thread when it's possible, and that's basically because it's more optimal to do so. You do not have to switch threads or contacts or whatever. This is the fastest way. Often these implementations offer several schedulers. So and most of the times they explicitly offer a scheduler for I/O operations, because these are operations that are expensive, right? We want to read data from an external system. This is an expensive operation in time, right? Because we send that we want to receive data, and then we have to wait for this data to come in, and all that time waiting, you cannot do anything else with that thread. So these I/O schedulers are basically thread pools in order to help you with that concern. Another one is hot or cold publishers. Anyone heard of the hot or cold publishers? Okay, so it's something that comes along in blog posts and whatnot on the internet as something that's really important. I don't know if it's really important. I've never had to make to discern the two, but basically they're about a cold publisher is one that will only start emitting items when it's subscribed to, right? So whenever a subscription happens, it will send data to that subscriber from beginning to end. And whenever you resubscribe, so you subscribe another one, it will again receive from the beginning until the end. And a hot publisher is one that actually receives events or produces events, and it does not buffer them or whatever. So you only receive the events that are being generated after you subscribe to it, and all the events that were generated before that time are lost to you, so you won't see them. So an example of this. So here I create a flux, which again basically does generate the numbers, right? So we've seen earlier. It's run on the Elastic scheduler, which is basically the whole thread pool for I/O stuff. And I will subscribe to it 2 times, and both subscribers will actually print out the items that were received, and we'll add them up or count them and tell them how many items were received. And I have added a bit of a delay between the subscriptions. So we subscribe one subscriber, we wait for a bit, and then we do the second subscriber. Now with a cold publisher, this will result in basically both subscribers receiving the same 100 items. Right, so subscriber 1 has received them, and then subscriber 2 has received them as well. Now when you have a hot publisher, and I create a hot publisher here by creating a connectable flux, which is a special type of flux which allows you to control the moment it starts emitting items. So you can subscribers to it, but it will not start emitting items right away. You actually have to tell it to connect the subscriber to the connectable flux, and then it will start emitting items. And in this case, I will connect it after the first subscriber has subscribed. So then it will start producing the events, and I will wait a bit, and then I will subscribe the second subscriber. And what you'll see is that subscriber 2 didn't receive any items at all in this case. Let me give it a bit more time. And now you'll see that, well, the publisher had already provided 45 items to publisher 1, and then the second subscriber was added, and it only received the remaining items. So that's the difference between hot and cold publishers. Working with resources, so one of the things that you often want to do in processing is, for example, is reading stuff from a file. And this works a bit different when working with Reactive Streams, mostly because of its asynchronous nature. So normally we would, by default, go to the try with resources construct that you have in Java, but this does not work for Reactive Streams. When we see it in action, so the try with resources, right? I start reading all lines from a file. This is this stream, by the way, is just a Java 8 stream, providing me with all the lines. I will create a flux from that stream and then subscribe it on an IO thread and print all the lines. When I execute this, I get an exception. And basically, I get this exception because this stream has already been closed. And this is because processing the whole flux in an asynchronous way happens, and we exit this try with resources block, and it's finalized, and the resource is closed. And then the stream is closed. And at that time, I want to read from it in my reactive stream, and it's no longer possible because the stream is closed, right? So that does not work. Now, you might be a bit smarter and say, well, you know what? Let's not do the try with resources block all around it, but we do it where we create the flux, right? We create this flux from a supplier which supplies us with the stream, and then we build this try with resources block around it. This does not work either, because what happens is this stream is lazy. So whenever the supplier is called, the stream is created, and the stream has not read all lines in the file at that point in time. It does not buffer it. It only reads them whenever there's something calling the stream to actually collect the lines. So when we run this, we get the same result. Again, it closes before it's actually been read. So all these implementations offer you a way to deal with files. So I will not show all of them to you. Let's only show the Rx implementation. But basically, it uses this using operator. So I tell the flux be created using a certain file, and then I create the flux from the stream. So this lines function will provide me with the Java 8 stream. This will create the flux for me, and then whenever the stream is done, so when onComplete is signaled, I will close the stream. So I have to do it myself in this case. And I subscribe again on the IO thread and print it out. So in order to show you that it works, okay, so basically this is just a file I took from, I think, Airbnb. Anyway, this way it works, and it prints out the lines. Another interesting, or perhaps a difficult thing to do whenever you work with asynchronous system is testing asynchronous stuff. Any one of you ever has to write unit tests while handling asynchronous things in code? Okay. Who thinks it's easy? Okay, well, me neither. It's always hard. It's always a problem. Now, luckily, with these Reactive Streams implementation, we get a set of tools in order to help us to make this easier. So RxJava offers you a test subscriber, Reactor offers you the step verifier, and Akka Streams offers you the test sources and test sinks, which are part of the Akka Streams test kit. Now, Akka Streams actually offers you even more in order to actually test with the underlying actor system. So you can actually look at the messages that are being passed and whatnot. But for us, that's not a concern at the moment. And testing these reactive streams often comes down to actually testing the sequence of events, so validating the flow of events, right? So I expect a certain amount of on-next events to be triggered, or an on-error event, or whatever, and I expect this stream to complete or not, in order to see if it works, actually it works properly. And these test tools often also offer you ways to manipulate time, which is cool, right? Manipulating time, that's awesome. And that's needed because, for example, when you have a publisher that emits items every, say, 100 milliseconds, or perhaps even a larger interval, you do not want to wait all that time for your test. That sucks. So what you can basically do is fast forward time fast forward time with the test tool in order to make this a bit faster. So what does this look like? Basically, the step verifier, which is created from the range flux, and it expects 10 items, and then it verifies that it's complete. The test subscriber for Rx. Basically, you create this test subscriber, you subscribe it to the flowable, the Rx flowable. You will assert, well, this time I also assert that there are no errors, and I assert that there's a value count, or that there are 10 items, and I assert it complete. Well, the whole test sync from Akka Streams, and this I didn't find a way to actually expect 10 items, but this way I specified that I expect first the item 0 to be emitted, then 1, then 2. So these tests are okay, and to prove to you that I'm not lying, we're actually testing something here. It breaks whenever I change the test, right? So this allows us, or offers us some tools to test these streams. Trickery and Witchcraft. So there are optimizations in these frameworks. Macro fusion, by actually saying, well, you use this sequence of operators, but I can do that more efficient in one operator, so I change the 3 for 1, for example. And microfusion in order to prevent copying of data. They are able to share resources. So under the hood of these implementations are actually a lot of these really nifty tricks in order to optimize the performance. It optimizes the thread and actor usage, and it eliminates the queues and boundaries. So in summary, the Reactive Streams provide you with asynchronous stream processing in a really easy way, I think. There are several implementations available for you, whatever suits your needs. There's a good interoperability between them, which is cool, because you can use technology based on the one implementation with technology that's based on the other implementation. And they're deceptively easy interfaces. Implementing your own is really hard. So I think we're actually done. So if you have any questions, you can both come up to me afterwards, and I will be happy to answer them. The code is on GitHub, so you can check GitHub out. I will tweet the slide deck. My Twitter handle is on the bottom right of the screen. Thank you for your time, and do not forget to vote. And when you're voting, be honest and be generous. Thank you very much.